It's April 2021, and behind me is the Nethermills weir, where we're going to put an Archimedes screw hydro turbine, which is going to power the Ayrshire College and the local area for decades to come.
At one time in history, the watercourse of the River Aire had 26 working mills along its length. Years in its imagination, planning and careful construction, the Energy Agency oversaw an exciting new project to bring the lower or nether mill weirs back into use, around 70 years after the corn mill here shut down. The Nethermills hydro scheme will not this time be providing energy for the milling of wood, paper, fabric or cereals, rather it will be providing clean energy for the nearby Ayrshire College. To realise the construction of the Nethermills hydro project, many challenges would face the team, including twice daily high tides and the unpredictable weather, plus the need to make something that fitted comfortably into the landscape of Ayr, minimising its ecological footprint and improving the habitat for migratory fish and eels.
For myself and the Energy Agency, all the staff involved, we are really excited about the beginning of this construction project. We've been working towards Nethermills hydro scheme for many years now, and we're just beginning the project. It's going to potentially provide carbon-free power for the college for many years to come. It will be an amazing demonstration project for many other hydro schemes across the country. And it'll help young people learn about this system.
Well, the most exciting challenge is presented by the fact this river can rise by 6 feet or more in the space of 40 minutes in the right weather conditions. So we need to install a temporary dam which will hold this back and keep the works and the engineers safe in the worst conditions.
It is the beginning of this really exciting project, and we hope there will be many more future ones to come. But at the moment, we're just very keen to be beginning it at this point. We were on site in 1999 with Finnish and German partners as part of a European project, and we said at that point, oh yes, we'll put a hydro scheme on this site, and it's a long time since then. So we are very pleased that it's now about to start.
In keeping with the ethos of the Energy Agency, its objective is to use local suppliers of services, materials and products as much as possible in order to minimise the carbon footprint of the project and to benefit the local economy.
A challenge of this green energy project is to carry it out without negatively and unduly affecting the sensitive biodiversity of the area. We have to carefully monitor the impact of the project on the local biodiversity.
The initial ecology, hydrology and design studies and the applications for grid connection and an abstraction licence had begun in 2016, and with the expert assistance of the Manpower Hydro Company, the crucial planning consent and preliminary accreditation for feed-in tariffs were obtained in March 2019. Important positive factors in making the project feasible were the good condition of the weirs and fish passes and the proximity of the college building with its big electricity demand. The challenge was constructing the scheme within the volatile and sensitive river environment.
In the hydropower business, the majority of the work that we do in the UK is with these low-head sites, which were mostly traditionally water mills. And so we're happy with the level of environmental risk from these schemes. It's not like the big dams which inundate an area and cause all kinds of knock-on problems. You're simply making use of what's there already, moving the water slightly from one path to another. And as I say, that seems somehow an appropriate solution. It seems it's something which people can emotionally appreciate. And plenty of people come to us with ideas for doing these projects. The question really is just whether, in their particular case, the economics stack up, they have a need for the electricity that can make it worthwhile to commit the investment.
So it's fantastic for Ayrshire Rivers Trust to be alongside the contractors and involved in this project here that will generate green energy that will help power the college, hopefully inspire the local community to enjoy the environment that surrounds them, and to probably further their understanding of how we can use nature in a sustainable way hopefully learn more about the fish populations that are right on their doorstep. And we've got a rough idea of what's going to be there, but you're never 100% sure all your species range, sizes, how many. So we get in there, immediately we see silt, we know we're going to get lamprey, there's undercuts underneath the concrete there, we know we're going to pull out some eels. There's a good chance we're going to have stone loach and minnows because they're fairly ubiquitous across the catchment. And I did have a bet with Muir that we wouldn't have trout in it, but we pulled out 2 small trout, so I'm down. But it's always very worthwhile coming onto a site like this, and it amazes the workmen to see what comes out of what looks like a stagnant little pond at the moment. So my colleague Muir will net the fish out, they'll go into a bucket to recover, I'll give them a few minutes and we monitor them, make sure that they've recovered from their little electric shock. And what we'll do then is typically we can measure them, we can look at what we've got, make a note of the species that we're removing, and then they can get moved into a safe environment and they can continue their life in there. So green energy is becoming a far more popular and obviously sustainable method of generating electricity, and it's an important means to be able to harness energy like this. And projects like this are about not damaging the environment and utilising green energy rather than ungreen energy, for want of a better word. And that's why we're here today and why we'll be back and forth over the lifespan of this project to make sure that things are going as well as they can do and that the fish are protected, moved out the way if needs be. But hopefully with the publicity that this project will generate, it will help inspire and the local public to really get involved with looking after their local habitat, and there's lots of ways you can do that.
The main challenge is going to be putting in a temporary dam across 1/4 of the weir, which will hold back the spate water and keep the engineers safe and dry throughout the construction period.
First thing we've got to do is we've got to mobilise onto site to create temporary access into the river to be able to start the works, i.e. installing a cofferdam, which means making a temporary dam in the river to work behind. It's quite a tricky site this, because we've got to deal with the elements of the tide to come in at us, so we've got that to deal with, which is going to be a challenge.
The downstream cofferdam at this site, where they were keeping the water out while they dug the deep hole and when they installed the screw into that pit once the concrete was complete, prone to particular risk because it's a tidal site. So twice a day, quite regularly, the water level rose and often threatened to overtop the cofferdam at the bottom end. The time-lapse photography shows this quite clearly. That's a particularly difficulty of working with the tidal site. Normally we know that we're only needing to watch the gauge for whether the river's likely to increase in flow upstream. But here we're doing both that and watching when the tide's coming in.
We've got the river levels to contend with on site, but hopefully we're mobilised at the right time of year to limit us risks in the water. But we're used to taking on these challenges and working in this environment, so we'll do as best, and fingers crossed everything will work out all right.
I think the biggest challenge that we have early on in the project is the construction of the dry dock that I'm currently standing in, and this is where the new hydro plant is going to be located.
We're going to use a trench box system here, which is large steel boxes which are lowered into position and bolted together, and then in between the trench boxes we line it out with a visqueen liner, and then we use ton bags with clean gravel to give it the weight in the middle to hold it all in place. So that's basically the method on this site for the cofferdam. So, and obviously then any sort of leakage we get through the temporary works, we have pumps in place to over pump out any ingress of water to keep the work site dry throughout concrete pours and what have you.
The downside is once water gets into the cofferdam in high river conditions, it's carrying a lot of silt, and therefore if it makes its way in and settles, there's more dirt inside the working area than you would have wanted, and you have to remove that material in order to be able to carry on. It's a particular danger if the cofferdam overtops during concreting works, because it can damage the concrete and you may have to then start again if the concrete is affected before it is able to set solid.
Amongst a number of unpredictable issues that the contractors are having to deal with is the discovery of a significant leak of water underneath the 14-year-old lower fish pass, which, as well as adding to the amount of diesel-hungry pumping out required, is likely to continue to be hollowed out and get worse over the coming years, potentially robbing the turbine of even more water and so energy. So a plan has been hatched to mould a large concrete plug to insert and close off the leak.
Yeah, we're going to have to install a temporary fish pass, because the bottom fish pass on the lower weir we're going to have to take offline for a period of time. So we've been working with SEPA and the Ayres River Trust to come up with a temporary fish pass design and installation that keeps fish passage open throughout the construction period, and we'll endeavour to get the bottom fish pass back online before the main salmon run towards the back end of the year.
There was an extension was made to some of the cofferdamming to make it slightly taller around the area of the fish pass by attaching some steel uprights and putting boards between those. They were steel uprights which I think they've been obtained from motorway crash barrier applications. They served very well and they can be reused elsewhere.
Can't be pumping out obviously any sort of like silty water, so we've got to have water management systems in place. Running through sediment tanks, straw bales that we create up on the dry dock area to allow it to flow back into the river in a clean as state as possible.
And the water which has to be pumped out of that cofferdam, it means that pumps have to be kept running 24/7 in the most critical phases. That water is then pumped out through filters into the river downstream of the site. So at these kind of hydropower sites, essentially you have to dig a hole in the ground in the river. And the difficulties with that are, well, you could find all kinds of things. So the contractor doesn't necessarily know before they start what they're going to encounter. In some cases bedrock, as at the downstream end of this site, and in some cases concrete, as at the upstream end of this site, and a load of silt which has settled there over time, as is often the case behind weirs.
Fighting against the time, tide, occasional high river flows and the weather, the construction team creating the reinforced concrete walls have to ensure that they meet the rigid scheduling of the concrete lorries, because any standing around costs money. By midsummer, the concrete housing of the Archimedes screw is completed. The perfectly level concrete floor of the main channel is where the feet of the Archimedes screw will stand. This required precision casting so that the screw can sit at the exact level and angle as designed to gain the maximum generating potential out of the flow of the river.
The contractors had to form concrete works to install the screw into, and those consist essentially of a rectangular concrete channel with a flat bed, then a vertical step downwards, and then another rectangular concrete channel below. So when the screw is installed, it's lowered down in its trough onto the two slabs at the bottom and the top, and those feet are bolted down into the concrete. So the trough is permanently affixed. The screw sitting in the trough is then mounted on its bearings and can freely rotate within the semi-cylindrical trough.
The bywash channel runs alongside the main channel for the Archimedes screw. This will be fitted with a large steel bywash gate which, when lowered, will allow the flow of the river to bypass the turbine to facilitate cleaning of its debris screen and for maintenance operations. The next part of the build is to create the concrete walls which will form the outside of the watertight powerhouse, which will house a generator and electrical equipment. The large steel meshes are carefully cut in place to make frames. Around the frames, fixed sheets of treated plyboard are carefully bolted into place. This creates a mould shape of the wall with the steel reinforcements running throughout it. The forms are tied together and supported with various struts to ensure that the structure is strong enough so that it supports the full weight of the concrete as it's poured in. Once the concrete is set, once it's cured, the shuttering carpenters strike the plyboard and take it off. The bolts that held it in place are removed, and any steel that sticks out is cut off, and the concrete is then finished to fill any holes where the bolts have been pulled out, so as to make it good so that it has a smooth surface. The challenge in a river and tidal situation is providing the concrete a long enough period of dryness so that it cures properly, achieving its maximum strength and therefore able to take a full loading. In late September 2021, the Scottish Government came to have a look at the project to see how it was getting on.
So Scotland's going to go through a major transformation over the coming decades, and it's projects like this here, innovative, ambitious little projects like this here, dotted all over the country that together are going to make a huge difference. So first and foremost, it's clean energy, and I think you're displacing or removing 147 tonnes of CO2 equivalent from the atmosphere, which is a valuable contribution. And also I think the students are going to be able to use the hydro for educational purposes, and at the local university of Western Scotland as well. You have to use the most of our own natural resources in Scotland to produce our own clean energy. And that's a huge opportunity, which clearly Scotland's been doing for decades, but now it's a climate emergency, so it's foot on the gas, forgive the pun, so we can have more projects like this. So it's a great showcase project for Ayr.
Yes.
And it's exciting how you're going to put the profits, so to speak, back into other schemes and tackling energy efficiency and fuel poverty. So I just want to wish you all the best and say clearly that we need projects like this, because in the news today we can see that with rocketing energy prices and gas prices, we have to use the most of our own natural resources in Scotland to produce our own clean energy.
The logistics for the delivering and the fitting of the mechanical parts of the hydro scheme provided a set of unique challenges. The hiring of the huge crane had to coincide with the arrival of the prefabricated Archimedes screw from Belgium, as well as the Archimedes screw covers, fittings, generators and parts of machinery. They all had to make the long journey from Belgium and overcome import delays caused by Brexit, plus have their arrival coincide with the erecting of the huge crane needed to lower the pieces of this large jigsaw into place.
The installation date, when all of the concrete works were complete and ready to receive the machinery, was the most nail-biting moment. It was necessary because it wasn't possible to get a crane to set up right next to the system, and the crane had to set up 30 metres, 40 metres further away. The size of the crane needed to be greater than we would have expected, and a 500-tonne crane was ordered.
On the day of the proposed lift, and up against tight time and money constraints, the Scottish weather delivered a perfect storm of rain, swollen rivers, high tidal flows, and the most challenging gale force winds. All morning the crews tried to assess if the winds were within the legal and safe limits for the lift.
Unfortunately, because the wind was too high, it couldn't lift for the first day, which was a concern to all involved because these cranes aren't cheap.
It soon became clear that the high gusts of the storm combined with the huge weight of the Archimedes screw meant that the lift was impossible. The forecast for the next day weather was also worrying, but the crew were hopeful that there would be some small window opportunity. Thankfully, the next day the winds had subsided enough for the team to decide that the lift could go ahead. The lifting crew oversaw the fitting of the huge bolts, ensuring that the hydro screw was ready and secure to be lifted. After a couple of last-minute ground checks, the huge screw was slowly lifted up over the trees. The highly skilled crane driver had to keep a close eye on every inch of the lift. Slowly, inch by inch, millimetre by millimetre, the screw cleared the trees and was lowered towards a concrete housing. With the help of the ground crew, the final few metres of lift was achieved. As it finally came to rest, an agonising set of small adjustments and last-minute calculations had to be carried out before the huge screw could be accurately aligned with the generator in the housing. Centimetre by centimetre, the driver of the huge crane, under instruction from the installation crew, made the minute adjustments necessary.
When it's installed, it's essential that the screw is installed at the angle which the supplier has intended it should be, because that affects the efficiency with which it can derive power from the water that flows into it. So on the install day, a lot of time is spent with the install engineers measuring that the interference of the screw trough feet with the concrete is correct.
And then suddenly the Archimedes screw was in place, and a collective sigh of relief and celebration was felt by everybody on the site.
With a little bit of adjustment, it seemed to fit quite well. So everybody was pleased.
Following the successful operation, steel housing and covers and huge sluice gates still had to be loaded into place and fixed. This required some last-minute fine adjustments to the concrete shell.
This is an exciting project because we contribute to a better world, to a greener world. We use the energy of the river flow to produce electrical energy which can be used in the houses, in the schools and everything. So that's why it's a fantastic project.
Well, this was interesting for us because it was our first time working with a new screw supplier, Van der Zande.
We produced this turbine starting from steel plates, from basic materials, forming the blades, forming the screw to a rotating body, turning here in the river. We have to take account of the normal behavior of the river. The river flow is varying throughout the year, the levels are varying. We are here on the seaside, we have the tidal characteristic of the lower bed of the river, so we have to take into account all this boundary conditions in order to design our screw. And then we have to do also the mechanical design. We have to make sure this turbine can turn over 20, 30, 40 years here, continue producing energy, taking into account climate change and all these aspects which are very important. Inside the turbine house we have the generator. That's in fact the heart which is producing the electrical energy, which is transducing the mechanical couple to an electrical current. So that's which is in the house, and the screw itself is turning around 18 revolutions in a minute, but the generator it's turning 1,000 revolutions in a minute. So what we do in this powerhouse, we transmit this 18 revolutions in a minute to 1,000 in order to be able to produce electrical energy. The biggest challenge was here in the design, because we only have 1.6 meter head, which is a very low head. So we had to put the screw under a very low angle. And here we put the screw under 15 degrees with the horizontal. And this is the first hydropower scheme we put under such low angle. So it was really an adventure to design this, but it works, and it works very good, and that makes us happy. In fact, this project opens doors for many other sites who are saying now, okay, our head is too low, we cannot find the technology to produce energy with the water passing here. My answer, yes, we have the solution, and we have a site who is doing it. The transportation to here was a real difficult job, because with the size of this screw, the dimensions, it was exceptional transport. We are coming from Belgium, so we have to pass the channel. I had to organize a ship, then we had to organize here the local transport, so there was no police to guide the transport on the local roads here, so it was a lot of organization and things like this. But once the screw arrived, we were all happy. Our people here, which has to do the mounting job, they had a little bit stress to fit in everything here on site. For sure, taking into account that we had to deal with the sea coming up every 4 hours. But after all, we picked the screw up, we put it in, and everything went very well.
Once the generator was fitted, it became imperative to get the roof onto the powerhouse to make it watertight and weatherproof. The curved design and the prefabrication technique required that the curved roof fitted exactly to the steel structure. Happily, the fitting went without any real technical difficulties, and in a single day in a perfect window in the weather, the roof was quickly fitted. At the same time, the construction team worked quickly on some last-minute snagging on the concrete walls in readiness to let the water of the river flow through the whole structure.
So having applied this semi-cylindrical cover, which must extend all the way up to the top of the blades and safely close them in, that dictates how the powerhouse can be designed to fit adjacent, because the screw extends up into the powerhouse where it has a watertight seal to keep out floodwater, so it must come quite close. The eaves of the roof are an important detail that has to be integrated with how this cylindrical cover approaches the powerhouse. And in this case, the eaves of the curved roof were able to be set just above the apex of the curve of the mesh guard, which looks quite pleasing from a distance.
With the screw successfully installed in its trough, the next task is to lower the 8-foot hydraulically controlled bywash gate into its channel alongside.
A bywash is just a channel for letting things around the side of a hydro scheme. In this case, the bywash consists of a tall gate, about 8 feet tall, which falls down like a drawbridge to let the water through if we want to allow water and branches and so forth to disappear past the scheme. It's operated by a hydraulic ram, which is about 10 feet long, which pulls the gate shut after when we need to close again. And that hydraulic system is fed with hydraulic oil by a machine inside the powerhouse, kept safely in the dry. The main sluice gate for the system is a large square of metal which rises up and down, pulled by a hydraulic ram. The slab of metal weighs about 5 tons, and it's 4.8 by 2.5 metres and 40 millimetres thick, so it's quite a substantial stiff plate which will keep out all of the water. When that's raised up by the hydraulic ram, it allows water to go through and into the turbine, and when it's allowed to fall, it completely obstructs water and prevents it going into the turbine. That again is operated by a hydraulic system with rubber hoses leading into the waterproof powerhouse, powered by a hydraulic power unit which pumps the oil into the ram and lifts the gate. Well, we know in this river, like in many rivers, especially when they're in flood conditions, they'll be carrying quite a lot of what they call coarse woody debris, which means tree trunks and willow brash, traffic cones and other things. That material normally would just flow straight down the river, but if we're taking water towards the turbine, some of it will come towards the turbine, and we do find that we'll catch some of the woody debris on the entrance, the intake to the turbine. So we put in place a debris screen there which will protect the turbine from the debris. Smaller pieces of floating wood and plant matter can go through the turbine with no problem, but if there are big forked tree branches, we need to stop those. They stop on the debris screen, which is then able to be cleaned. It needs to be raked off. The pieces of wood need to be lifted out. But we have a mechanism on this scheme where if we close down the machine and open a bywash gate next door to it, the material which is trapped on the screen can be flushed off and drawn around the side, and that will escape downstream and into the sea. That can happen if the water's too high because there's a flood level, or if the water's too low and it's dry in summer conditions and we want to protect the river by leaving the small amount of flow there is in the river for the weir and for fish to use the fish passes. We include pressure sensors in the water, both upstream and downstream of the turbine, and also one right at the entrance to the turbine to constantly measure how high the water level is. That feeds into a computer, a PLC, in the control system for the turbine. And we're able to monitor and take that feedback and adjust the speed of the turbine so that the turbine can slow down and take less water and maintain the consistent level of the water upstream. If the level can't be maintained, we switch off, and that means we drop the sluice gate, immediately cutting off the supply of water. The water is left in the river instead. Well, this is a waterproof powerhouse in order to protect the equipment within, because we know the water level will rise, and that's not unprecedented. That we've done 5 or 6 of these around the UK. But in this particular case, the client was keen to have an interesting roof which would help the scheme blend into the local landscape, and therefore ordered a roof with a curved feature, a curved profile, which is covered in a sedum layer with some irrigation piping in it so that the sedum can be kept moist during the dry months.
The curved roof of the waterproof housing was fitted with a sedum roof. This comprised firstly of a waterproof layer. On top of that was installed a rooting membrane, a big map so the sedum roof, when it was rolled out like turf, could actually root and stay secure on the roof. Once a sedum roof has established itself, it's more or less self-perpetuating, and it can further develop and maintain itself. Roughly speaking, the extensive green roof has a substrate thickness of between 4 and 15 centimetres. Sedum's natural characteristics make it a plant as eminently suitable for a green roof. The sedum plants, which store water in their leaves, can tolerate drought and are very hardy. The sedum roof will also let the hydro project sit comfortably in the natural environment that has been created within. Plus, the sedum plants may attract bees, butterflies, moths, and other nectar-hungry insects.
So on this project, Marine Scotland were also interested in installing a fish counter and camera array on a fish pass which already exists here. The project to construct the Archimedes screw scheme allowed them access to get into the river to do that work towards the end of the construction project, and that's now complete, and they seem to be happy with that. It consists of 3 cameras and a resistivity counter which measures disturbances as the fish pass and therefore counts the fish. So they have both a count of the number of fish and a visual recognition of which fish they were that were passing, moving on their migration upstream through the site.
So we've put in a salmon and sea trout fish counter. It's a resistivity counter that basically monitors the electrical resistance of the channel that they're swimming through, or the fish pass. And when a fish swims through, it's much more conductive than the river it displaces, and the counter detects that change in resistivity. So we've also installed a number of internet cameras, IP cameras. So we've got an overhead camera on the frame behind that looks down on the fish as it passes through, and that gives us an indication of the size of the fish. We've also got 2 side cameras which are underwater and actually can see and give us an idea of whether it's a salmon or a sea trout. It's not always that easy to tell, but we've got some really, really good images here. We're very pleased with them.
And we're very pleased that this scheme is up and running now. We're getting counters into the fish passes, and this is going to be incredibly important for fishery management. It will allow us to have an accurate count of the salmon coming into the river, hopefully sea trout too, and from that we can help determine the appropriate conservation measures for the river. And it can only be good for management.
There are also tiles here, plastic tiles, set in runs to provide a kind of ramp for eels to get up past this weir, and a similar array with different tiles for lamprey. Both river and sea lamprey might come up past these weirs, and they prefer to have a shallow, fast flow of water with some pegs or features to get a hold on so that they can interrupt, take a rest and continue passing upstream. The fish pass which is here already is a Lorinier type fish pass consisting of metal baffles set in the bed. The water falls down over those baffles and it provides slow spots so that fish attempting to swim upstream again can pause, take a rest and then move on upwards. I was standing next to it yesterday when I saw a 9 or 10 inch trout pop out the top and swim off away upstream. So I can attest that it actually does work.
It's a good idea because when you make a big change on a river like this, at a barrier to migrating fish, it just gives you a bit of evidence that the fish are still getting through. It's also an opportunity to start to understand better what numbers of fish we've got. There's no data on it other than fishing data so far, rod catch data. So this will actually give us some hard facts as to the number of salmon and sea trout migrating up the river. And also a big concern around that with climate change, etc. at the moment and numbers depleting. We'll be able to see it over the internet, so obviously be able to view the cameras here, but we'll be able to log in remotely as the other interested parties will be able to. We'll be able to collate snippets of video from fish and publicise them, etc. So information will be available.
So because of Marine Scotland's fish counter, they felt that it was necessary to have some sort of safer pedestrian access for maintenance to the fish pass. And so as part of the scheme we've designed in this concrete walkway next to the pass and designed the top of a new piece of weir crest so it provides a continuous walkway. They have then added safety stanchions and rails to protect their maintenance personnel, which can be removed so that they don't act to trap debris or obstruct the river in high water conditions. Often we're able to build these schemes beside the weir and beside the river, and therefore the construction is a lot simpler. And in that instance as well, access into the system for the operators is fairly straightforward. They just walk in through a door. But in this case, because the scheme is built within the river channel, it's necessary to form some kind of bridge between the solid bank and the powerhouse and the sluice, so that the operators can make their way to and from the powerhouse. At this site, because we wanted to minimise the impact on any flood risk in terms of holding back the river in flood conditions, we designed the scheme to sit quite low in the water, and the access deck too is set down, so it's accessed from the bank by a set of steps behind a security fence. That means we had to design mesh walkways for personnel to make their way around the site at the right level for the powerhouse, and all of this is to be usable in the majority of the year. However, there will be a period during the year when it's underwater because we've kept it very low, and in high water conditions water will flow over the access decks. The powerhouse door is a ship's door which is waterproof to prevent the elevated river levels from getting into the powerhouse, so we're happy with that method. The hydropower control system is connected directly into the college by 100 metres of underground cable. It supplies electricity at their meter point, so if they're in a position to use that at any given time, they will do, rather than buying in electricity.
But here we have this initiative that is generating electricity for the college in Ayr and also going to the grid, which could generate electricity for local housing. And I think as we move towards being net zero, that we have to look at these kind of inspirational projects and roll them out in other local authorities and across Scotland.
We're renewable energy. It's going to a local community college. They're getting a very good deal on the back of it. It's looking at sustainability, and it should be a catalyst to learn from it. Timing wise, there's lots of funds going into it, so there's a lot of positive investment into the local community, and there should be a lot of positive outcomes coming out of it. And the feed-in tariff obviously made a big difference in making this scheme viable.
The electrical connection for a smallish hydropower project like this is not typically complicated. What we're doing here is we're connecting behind the meter of a local organisation, the college, who have a need for the electricity. And so effectively it's equivalent to if you put solar panels on your own house and feed them through your own meter. The difference being that with something of this size we have to talk to Scottish Power to agree the connection with them.
It's that local power is key. It's really important, and it's all about balancing things out. So you've got an energy source right next to the energy usage. Yeah, you need to have more of that going forward. We need to see more locally sourced energy as part of the wider sort of decarbonisation of the grid. So from a Scottish Power perspective, projects like this can only be seen as a good thing. It's part of the journey to net zero, and it's helping to promote the works that the Energy Agency does throughout the local communities, and that can only be a positive thing.
The quality of the power we're producing is controlled in our control system, which keeps things within certain parameters. So the frequency with which and the voltage at which we're delivering power to the college's meter is the same and compatible with the grid. All such systems have to be connected behind what's called a grid protection relay, G59 or now G99 relay, a switch essentially which has settings whereby if what we're doing is not acceptable, it immediately cuts off the connection. And likewise, if there are problems with the grid or a power cut, the relay cuts off the connection so that we can no longer produce power and put their engineers at risk if they had to come and fix the grid.
This is the most brilliant project. It's been many years in the development, and we've involved a huge number of partners. The project has been on track. There's been a huge amount of care taken to work with ecologists, fisheries professionals, archaeologists. It's amazing from the college's perspective because it can be used as a demonstration project to train young people in hydro schemes for the future.
It's been fantastic all the way through to see the construction, because it's been a great source for our students who obviously just study yards away from it. So we've got foundation apprenticeships in civil engineering, we've got the construction management students, we've got construction students, and they've all been able to see the project being constructed, they've been able to see the story of it, and to see it all tied together and working now is great inspiration for the future. We run renewable energy courses as well, so it's just fantastic that we've got this on our doorstep.
The programme has been of interest to us in the college. We in the college have been doing a programme in green technology, renewables technology and agricultural technology for a number of years. Well, the engineering department as it was has been operating for more than a century. So we have a big history in land use and including water courses for farming efficiency improvements. So I was in meetings for many months and years listening to the chat about using the water here at the River Aire for power, for green power. So it ticked every box for us in a teaching sense and in a practical project sense.
We've been working on site for a year now, but the end result is a very compact building with a very beautifully constructed Archimedes screw. And so the impact on the fisheries and the environment should be very minimal while producing carbon-free power, electricity for the college.
It's so important because our energy crisis now is such that all our renewable energies have got to be put to exploited to the maximum in order we can make more meaningful energy policy. And this is quite small by comparison, but it's a start, and it should be a pointer for others to think in this direction.
Yes, Scotland's leading the way. It has been for many years, and I think we will continue to lead the way. And I think that what governments need to do is look at different models around the world, but also look at Scotland. And I think that we just have to look at these projects and invest in them.
So for the long-term future, this should last for the next 40 or 50 years, providing really carbon-free electricity which will help power the college. It's an amazing demonstration project for everybody else. We've had people from Wales, we've had people from Ireland coming to look at it to discuss what they might do in their own environment. Archimedes screws are used all over the world for different things, but there are still very few in the UK, given how much water that we have and how many suitable rivers. So it's really, we're hoping that this is the beginning of many more schemes throughout the world, but particularly locally.
In the greater scheme of things, this project that we're developing here on the River Aire might seem quite small, but we believe it should lead to more progressive national policies in response to the current energy crisis and climate emergency. The hydro scheme is also making an important contribution to Ayrshire College, not just in terms of the green energy it receives, but also for the education resource it can provide to its students. All profits from the electricity sales from the hydro scheme to Ayrshire College will be put into a fund which will be used on energy saving projects and projects that help combat fuel poverty. I'm very proud of what our organisation has created here for the future benefit of Ayrshire and the wider community. We hope it might inspire other groups, communities and organisations to take a closer look at what they can achieve in their own particular situations and circumstances and help towards a sustainable future. The Energy Agency hopes that this project will motivate and inspire other organisations to think about hydropower again.
Well done to the Energy Agency. This has been a really long-term project which they've been dedicated, and I know there's been over £1 million of funding. It's been a really difficult project, but they've delivered it. It's here in Ayr and we're generating electricity for our college, so well done, it's fantastic.
In February 2022, after many years of careful planning, of building an open-minded international and imaginative team, of overcoming multiple financial hurdles and challenges of rain, wind and tide, the impacts of Brexit and a global pandemic, having employed the services of 30 local businesses and only a month behind project schedule, the Nethermills hydro scheme was declared open and began generating green electricity for the Ayrshire College. The project is generating electricity and all manner of fresh data on the links between patterns of rainfall, power generation and local consumption, and on the fish populations and their movements. The Energy Agency hope that this local project in Ayrshire will inspire many other regions to consider adapting innovative renewable energy generating solutions suited to their own unique situations to benefit the environment and future generations. Members of the local community say they love the way the hydro scheme blends into the landscape and are proud to have such a carbon-friendly and green project alongside their much beloved river walkway.